Let's recall what we did last time. Last time we did projections. Okay. We first introduced how to project a vector onto another vector. Okay. This is easy because it's one-dimensional. So if we subtract a vector by its projection onto a vector, then the remaining part will be orthogonal. Orthogonal. Okay. You know, projection is an operation that you plug in a vector, output a vector. So we can also achieve this map by multiplication of a matrix. This is the projection matrix. And last time we determined the projection matrix for projection onto a line, okay, onto a vector B, okay. Now, if we have you know a vector space, we may need to project to a subspace of this vector space. So this is the second part. How do we do projection for onto a subspace? So this is what we are going to talk about today. Projection onto subspace. Okay. Projection onto subspace. Now we already know how to project it onto, you know, one-dimensional vector space, you know, project onto a vector. Now to project onto a subspace, well, we need to consider basis of this subspace. So suppose let U be, capital U be a subspace of a vector space V. Okay. Now the idea, now we want to find the projection onto the subspace U, okay, given a vector in V. Okay. Now the idea is we project onto an orthogonal basis of U, okay. Okay, there are two ways to do this. Either we do it like this. Suppose we have a basis. If we have a set of orthogonal, be careful, orthogonal basis. So suppose it's U1, U2, UN. So this is basis for the subspace U. Okay, the subspace U is dimension n. Okay, and we can for each vector U1, U2, UN, then we can find the projection matrix onto each vector. Okay, now we can find Q1, Q2, Qn. These are projection matrix. Projection matrices. Okay, onto U1 UN respectively. Then the projection onto the subspace U. Then the projection let P. Then the projection matrix. Matrix onto U is given by the sum. The sum, okay, is given by sum of this Q2 sum of the projection onto its vector. Okay, it's orthogonal. Now be careful. Here we need to make sure the vectors, the basis vectors, should be orthogonal. should be orthogonal. Okay. Okay. Example. Let's see one example. To explain the idea. Okay. Now suppose we want in R3, V is R3, U is the XY plane. U is the XY plane. Now we project U on V. We project a vector in R3 onto the XY plane. Now any vector V in V, for instance, we write V as X, Y, Z. Okay. Now to project this vector V onto the XY plane. This is X, Y. This is Z axis. Now suppose we have vector V. Okay, this is V. Now you find the projection onto the XY plane. You find the projection onto the XY plane. Okay, now the projection of V onto the XY plane will be, so let me plot it in color. Okay, this will be, let's use plot it by red. So the projection will be red. Okay, the projection will be red. Now, if you project onto X, you project onto Y axis. You will see, let's use X be green. Projecting onto X, you project it onto X, then you get the green part. And you project onto Y, you get another color. Let's see, let's use blue. Okay, this is projected onto Y, and then the green is projected onto X. We project it onto X. Okay, now you see the projection onto X plus the projection onto Y is a projection onto the XY plane. Okay, so the projection, now of course, XYZ, we project it onto the XY plane. So this will be XYZ. Let's use column vector. So XYZ projects onto XY plane. So the height will be 0, okay? So this will be X and Y, they are fixed. The height will be 0. So projection onto the XY plane. Now the projection onto X, V, projection onto X, so this is the PXY. Project onto X-axis, this we get X, 0, 0. Projection on V, on Y-axis, so this is PX. X, Y, Z, then we get projection onto X-axis, Y-axis, we get 0, Y, 0, okay? Okay, this is projection on Y, okay? So that's easy, now we can write down the projection on X, the projection on Y. So the projection on X, you can write down. That's easy. We, according to what we did last time, we can just write down directly. So it's 1, 0, 0. Okay, 0. And PY, the projection on the Y-axis is 0, 0, 0. It's 0, 1, 0. So this is projection on Y. Now the projection on XY will be PXY. This will be PX plus PY. So this will be 1, 1, 0, 0, 0, 0. Then all others are 0. Okay. Okay. So this is trivial example. Okay. Now let's see this example. Example. Now let U be this subspace. Let U. Now it's possible that you have a basis that is not orthogonal with each other. Be the subspace of R3 generated by spanned by these two vectors. U1, which is 1, 1, 0, U2, which is 0, 1, 1. Now you can check the two vectors are not orthogonal by taking dot product. Okay, so they are not orthogonal. So we cannot directly apply the projection onto its basis vector. Now we need to make sure we need to generate an orthogonal vector with other. Well, what we do is we fix one vector u1 and then we manipulate u2. Manipulate u2. Then we get the orthogonal basis of the subspace u. So we choose E1 to be just U1, which is the 1, 1, 0. Now we choose E2. Now we subtract from U2 the component, the projection, subtract the projection of U1 in on the vector U2. So the projection of U1 on U2. This will be U2 dot product U1. Now we know how to do that. We know how to do this according to the projection onto, projection of vector onto another vector. Now this will be U2 subject. This is very easy. U1 you find U1 norm squared sum of the components 1, 1, so it's 2. Now U2 dot U1, you find this actually really easy. It's 1, very easy. So this will be 1/2 minus U1. So this you get U2 is plugging U2 and U1, 0, 1, 1, subtract 1/2, 1, 1, 0. Now this you get, finally get 1/2. Do some algebra. That's easy. 1, 1, 2. You can believe me. Okay, so then we find the projection on U1. So E1, E2 are perpendicular now. Okay, by this construction, E1 and E2 they are perpendicular, and they spine the same thing as U1 and U2. Okay, so we choose U1, U2 as a base. So E1 and E2. E1, E2. So E1, E2 spines. This spine the subspace U. Also spine the subspace U. Subspace U. Okay, because E1 is the combination of E1, E2. They are both linear combination of U1 and U2. So this spine, they also spine U. Okay, spine the subspace U. Okay, and also we check that E1 dot product E2 they are orthogonal. So we can use projection on E1, E2. So Q1, by the projection formula for one, for one along one vector, this is U1, you use E1 or whatever, E1, U1 the same. So it's E1 times E1 transpose divided by E1 normal squared. So E1 is just U1. So this is U1 1, 1, 0, and then it transpose 1, 1, 0 divided by E1 normal squared, which is 2. So this is, you get 1/2, denominator 1/2. So you just write the 3 vectors 3 times according to the multiple 1, 1, 0. So it's 1, 1, 0, then 1, 1, 0, and then the last is 0 multiple, so 0, 0, 0. Okay, so we get the projection of a projection matrix onto the direction U1 or E1. Now we do the projection onto E2. Q2, this will be E2 times E2 transpose over E2 normal squared. So this will be, you plug in, okay, E2 is 1/2 negative 1, 1, 2 times 1/2 the transpose negative 1, 1, 2 over E2 squared, E2 normal squared. Remember, you can find, we know the E2 component. Okay, we know we already solved E2, which is the 1/2 negative 1, 1, 2. So this is E2. Okay, this is E2. So we can find its norm easily. So somehow you find it's normal. Okay, it's a 1/4, 1/2 squared. Its coefficient is -1 squared plus 1 squared plus 2 squared. So if you work out this, you finally you get 1/2 times 1/2 cancel this 1/2 squared. So you get 1/6. Now the matrix multiplication, rule column times rule. You can either use column picture or rule picture. You can repeat the 3 columns, okay, 3 columns according to the multiple of -1, 1, 2. Or you repeat the rule -1, 1, 2 3 times according to the multiple of -1, 2, -1, 1, 2. Okay, either you get. So let's use the rule picture. Then you get -1 multiple of the rule column, rule vector -1, 1, 2. So you get 1, -1, -2. Now the next is multiple 1 of the vector. So look at the second component of the column vector. Okay, second column, second rule. So so the second rule, you see the second rule is 1. Second rule is 1. So 1 multiply the rule vector. Okay, so we get -1, 1, 2. Okay, now the third rule of the column vector, let's use green. Okay, you see the green is -2, and then multiply the rule vector again. So we get a 2 multiply the red rule vector. So get a -2. Sorry, okay, negative, yeah, it's 2 and then 4. Okay. Okay, so we get the projection of Q2. Then we add the projection together, so that the projection onto U is the projection matrix Q1 plus Q2. So Q1 plus Q2 gives us the projection onto. So you can add them together. So let me just directly write down the result. So we write the component wise, add them together. Then what you get is 2/3, 1/3. You can try this. So you can believe me, add this 2 matrix together. So this is what you get. Or you factor out the 1/3. Is maybe make life easier if you factor out 1/3. Okay, so if you factor out 1/3, so this will be 1/3. 2, 1, -1, 1, 2, 1. -1, 1, 2. So this is the projection matrix. Then we are done with the projection matrix. Okay, another way to do the projection is now find the perpendicular component, complement, orthogonal complement. Subtract the projection onto the orthogonal complement. Okay, so another method. So we can solve this problem using another method. So we find the orthogonal complement. Okay. So we find the orthogonal complement. So in this problem, we are doing the vector space is R3. Now U1, U2 span a 2-dimensional, a plane. Now the orthogonal complement is a direction that's perpendicular to the plane. Okay, so we need to find a vector that is perpendicular to U1 and U2. Perpendicular to U1 and U2. So you check. It's very easy to check. Okay, for instance, V. So this vector. So let me copy U1, U2 here. So U1 is 1, 1, 0. Now U2 is 0, 1, 1. Now you can directly check we can find a vector that perpendicular to both. So for instance, if you choose this one, y, negative 1, 1. Okay. Now you can directly check. You can directly check by dot product. By dot, that's easy. Okay. You can check v dot product u1. You get a 0. We got a 1 plus negative 1. Get a 0. And v times u2. You get negative 1 plus 1. You get a 0. So v is perpendicular to the subspace u. Okay. So we get u is perpendicular. Sorry, v is perpendicular to the subspace. U. Okay, because u is spanned by u1, u2. Now you see, the linear combination of v is the orthogonal complement. Okay. So the orthogonal complement is in the direction of v. Okay, so now so lambda v. So this is lambda in R. This is the orthogonal complement of u in R3. Okay. Now we project the vector. We find the projection matrix onto the component. Onto the complement, orthogonal complement. Then we subtract that thing by identity. So projection matrix onto U. This will be the identity matrix I3. Subtract 3 by 3 matrix. Subtract projection on projection matrix. So projection matrix on on V. Here we already know V, the vector V is perpendicular to the subspace U. Okay, so we can write down the projection on V. So let's see, this is suppose this is we assume the projection on V is P. So we can write down what P is. Last time we already know projection onto one-dimensional subspace. So P, the projection onto V is V dot V transpose. So this is matrix multiplication, not dot product. V normal squared. Now you can easily find. So the 3 component of V is 1, negative 1, 1. So the V normal squared is 1 squared plus negative 1 squared plus 1 squared. Now, so you get a 1, negative 1, 1 times 1, negative 1, 1. Okay, so this you get 1/3. The denominator is 1/3. Now the matrix, what you get is, you can repeat the rule. So according to the multiple 1, negative 1, 1. Okay, so you get a 1, negative 1, 1. So we repeat according to the first rule. So we use the red, the rule vector. Now you see the multiple. What is the multiple? Let's use some color. So let's use green. Okay, the green. So 1, the green part 1. So we just repeat the red vector by the multiple 1 in the green. Okay, in the green circle. So we repeat that according to the multiple of the green. Okay, so now the second rule vector, we use another color, purple. Okay, so it's negative 1. So we repeat it, the rule vector according to the multiple negative 1. So we get a negative 1, 1, negative 1. And then the last, we use another color. Let's see, use yellow. So it's yellow is 1. So we just get multiple for yellow is 1, negative 1, 1. Okay, so this is a projection onto the orthogonal complement of U. Now to recover projection on U, we subtract. So so projection onto U, projection matrix for the projection onto the orthogonal complement onto U is, so the identity matrix I3 minus P. So this you get identity is y. So the all others are zeros. Subtracts 1/3. You copy that thing again. Y, negative y, negative y, negative y, y, negative y. So the diagonal thing, don't forget the 1/3. So you get 1/3. If you multiply 1/3, the diagonal of the identity will be 3, 3, 3 now. Subtract the diagonal of the other matrix. So this will be diagonal will be 3 minus y. So 3, 3, 3 minus y. So you get 2, 2, 2. And then all others you can easily find. So you get here y, negative y. So flip the entry of the second thing, second matrix. So off diagonal you get this thing. Okay. So here you get negative y. Okay. Now if you compare, what we get the result you see is this is exactly the same thing as what we get for you see this result. We project on each. Ooh, where is the result? Okay, here it is. Yeah. So this matrix, let me make it bigger. This matrix, this projection is obtained by we projecting onto each the two orthogonal vectors. We use projection matrix for two orthogonal vectors and add the two projections, and then we get the projection onto the subspace U. Another way we you see this matrix, we get the same matrix. Of course, we get the same matrix. You see, you check it with yourself. These two matrices are the same. Okay. So this we project onto the orthogonal complement and use identity to subtract the projection. Okay, so the general thing is if you if the orthogonal complement is easier, his lower dimension is easier to project onto the orthogonal complement. Okay, so if you have a space subspace U, so suppose. So the idea is if you have a subspace U, subspace is a subspace of a vector, let's see, V. Okay, so you can get a projection on, if you have projection, if we have orthogonal basis, if we can find, if V1 Vm is a basis, orthogonal basis. The keyword is orthogonal. It can be wrong if you use a non-orthogonal basis. So it's orthogonal basis of the orthogonal complement. So of the orthogonal complement, U complement. Then let P1, Pm be the projection matrix. Onto each direction, okay, each vector onto V1 Vm. Okay, then the projection on, so then P1 plus plus PM is the projection matrix. Projection matrix onto U orthogonal complement. Then we use identity so the projection. Then identity. You use the right dimension identity. Subject P1 plus plus PM is a projection onto U. Projection onto the subspace U. Okay. Now, if you have, so if we have, if we have U1, the vector U1, U2, so let this be a basis, UN be a basis, be orthogonal basis. A set of orthogonal basis of U. Now we already, so let Q1, Q2 be the projection. Qn be the projection matrix onto U1, U2, UN. Now we have the completeness relation. So the projection on U plus the projection on its complement or orthogonal complement P1 plus PM. This is the identity. Okay. So you add all possible projection for each orthogonal dimension. Then this is just the vector itself. So this is called completeness. Completeness relation. Okay. No component is lost. Okay. Now we know how to project onto a subspace now. Okay. So homework for this section. Now you should know how to do a projection. Here, there's only one question left. Now, if you have a vector space or subspace generated by a certain set of vectors, how do you find a set of orthogonal bases? Okay, how do you find a set of orthogonal bases? So this is what we're going to do in a minute. So homework, this thing, section 4.2 is number 1, 3, number 5, number 5 to 7, 5, 6, 7, 16, okay, 17. So this is homework for this section 4.2. Now we talk about the question: how do we find orthogonal bases giving a generating vectors or giving a basis? Okay, so this is the method called Gram-Schmidt. Okay, now we talk about this section 4.4, orthogonal bases. Not Gram-Schmidt. Okay, so the question is the following: given a set of vectors, linearly independent vectors, how do we find Okay, given a set of vectors, how do we find a orthonormal basis? Question. Given a set of vectors, linear independent, of course. So if it's not linear independent, we find the minimum number of generating vectors. So we throw out 13 redundancy linearly dependent vectors. Okay, let's see. The set is S. It has vectors, linear independent vectors v1, v2, dot, dot, dot. Let's see vn. So these vectors are linear independent. Now the goal is, how do we find an orthonormal basis? Find an orthonormal. So first, this is perpendicular with each other. And second, this will be unit vector. Of the space V, which is the spine of S, spine by S. Okay, so this is called the Gram-Schmidt method. The idea is we subtract the projection. So U1, we just, let's see, we want to find. So first of all, V1. We start V1. Now we so V1, we fix the direction of the V1, then we normalize it. So we make it to be a unit vector. U1 to be V1, the vector V1, divided by its norm. So this will be, then this we get a unit vector. Okay, unit vector. Now we do for U2, for V2, we subtract the projection along U1. Okay, so we subtract. So for U2, we subtract its projection on U1. So this be okay, sorry, it's a V2. So we are given the vector V2. V2 subject V2 dot product with U1. Now U1 is already unit vector, so this is a U1. Okay, so this is a projection of V2 along the direction V1. Okay, now this is a vector that, so W2 define. So this, then we already know W2 is perpendicular to V1 or U1. Now we need to make sure that W2 is a unit vector. So we renormalize it. So we let U2 be the vector W2 divided by its norm. Then this will be a unit vector. Okay, unit vector. So again, we get a unit vector that, by definition, U2 is perpendicular to U1. Okay, U2 is perpendicular to U1. Now for U3, for V3, we subtract the projection of V3 along onto U2 and onto U1. So this is the V3 dot U2. Now this is the projection on U2. Now we subtract the direction minus the projection of V3 on U1. Okay, V3. Now the projection, I mean vector projection. Dot product with U1, the multiply direction vector U1. So this we get W3. W3 is a vector that perpendicular to U1, perpendicular to U3. Okay. Then we normalize W3 by, so we get a U3, which we get W3 is a vector W3 divided by its norm. Divided by its norm. So U3 will be W3 divided by its norm. So it's a vector W3 divided by its norm. It's W3 divided by its norm. W3 norm. So we get a unit vector U3. So this U3 is perpendicular to U1, U2. So U3 perpendicular to U1, U3 is perpendicular to U2. Okay, etc., etc. So the Wn. So Wn. Now in this manner we get W1, W2, W3, Wn. Then Wn is the vector we subject the vector Vn. Subject the Vn subject the projection of Vn on its vector. That's Un minus 1 times Un minus 1. Minus subject, and then subject the projection onto U1. Okay, because we already subtract the projection, so this is actually a vector that is perpendicular to U1, U2, Un minus 1, etc. So this, and then we let Un normalize it. Okay. Okay. Then we have this Un is unit vector and Un is perpendicular to U1, U2, Un minus 1. So this is unit vector. Unit vector. So U is unit vector. So we also have Un times Un minus 1 is 0. Un times U1 is also 0. So Un is perpendicular to all other vectors. So this way we produce a set of, orthogonal, also normal pieces of the vector space. Okay, let's see some example. Any questions? Okay, let's see one example. Let's see this example. Now, of course, this way, now if you rearrange the order V1, V2, Vn, now you may get different also normal bases. Okay, also normal basis is not unique. You can find another choice. So the choice is not unique. So V1, let's see, V1 is 1, negative 1, 0. And V2 is 1, 0, negative 1. V3 is 1, negative 1, 1. Okay. Okay, you can check that they are not perpendicular. They're not all perpendicular. Okay, so actually this problem is easier because here V1 and V2 they are perpendicular. So if let's forget this information, you can check V1 and V2 and V3 they are perpendicular. But suppose we don't know that. If you change a little bit, you get a different number. You don't know it's perpendicular. Okay, so the first step, U1 is V1 divided by V1 norm. So this will be V1 norm. So this will be 1 over square root 2, 1, negative 1, 0. Okay, now W2. So W2 will be V2 subtract V2 dot product U1 times U1. Okay. So you can work out V2 times U1 dot product. You can write down the component. Okay. So you got this is easy. You can believe me. So you got 1 over root 2. Use dot product. Okay. Dot product is easy. So V2, you can easily check. This can be easily checked because we already have coordinate form, so we can find dot product. So you can believe me, we get this result. So this we get V2 is 1, 0, negative 1. Subtract 1. So the dot product is 1 over root 2. And U1 is 1 over root 2, 1, negative 1, 0. So what you get is, work out this by algebra. So you can believe me, you get 1/2, negative 1. So U2 is normalize that thing. U2 is W3, W2 divided by its norm. So you have coordinate, so you can write down everything. So this will be square root 1/2 squared plus 1/2 squared plus 1 squared. And then W2 is 1/2, 1/2, 1. So finally, what you get is work out this by algebra. So you get 1 over square root 6, 1, 1, 2. Oops. Okay, so we find U2 already. Okay. Okay, then we find W3. Oops. Okay, W3 is V3 subject V3, the projection onto its component U1 and U2. V3 U1 times U1. Okay, this you work out, this you get V3 is 1, negative 1, 1. And this dot product you can find is to be this dot product is root 2, and this dot product is negative 2 over root 6. Okay, so what you finally get, this is U2 is 1 over root 6, 1, 1, negative 2. And this you get U1 is 1 over root 2, 1, negative 1, 0. Okay, so finally you get, this is the 1/3, 1/3, 1/3. So you normalize it. So you get a U3, normalize it. Normalize W3 by its norm. So finally you get, this is 1/3, 1 over root 3, 1, 1, 1. Okay, you can check. Now this is indeed the 3 vectors. Let me write down, you check. So U1 is this, and U2 is, let me write down the 3. U2 is, you check that this is unit vector. So you can check that dot product is 0. Okay, and U3 is root 3, 1, 1, 1. You can check the 3, they are orthogonal to each other and they are unit length. So we are done. Okay, we are. And the choice is not unique. The choice is not unique. Now for this problem, if you observe that actually we have easier method. If you observe that the last 2 vectors U2 and U3, they are actually perpendicular. So you can choose that thing, and then subject manipulate V1. Okay. So this vector V2 and V3, you can check its dot product. Actually, they are perpendicular. But then you just subtract V1, the projection of V2, V3 onto V1. Then you, this will be easier. Okay. 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 Now, if we another thing that I want to mention is we can actually now if we have a bunch of bases in column vectors, so we can write this Gram-Schmidt in matrix form. Okay, in matrix form. So in matrix form, it will be tedious, but however, this is in matrix form. Gram-Schmidt in matrix form. In matrix form. Let's write the thing as matrix. Okay. In matrix form, the Gram-Schmidt method will be this. V1. So we are giving V1. Vn. Remember, they are linearly independent. So this is actually invertible matrix. This is the invertible matrix because they are linearly independent. Now this is U1 dot 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 UN. Oops. Times this matrix. Okay, times this matrix. Okay, so yeah, this should be this U1 dot V1. Here U1, U2, UN, they are orthogonal. They are orthogonal and unit length. Okay. So here this to be okay, this will be U2, V2 dot product. And here this thing is UN, VN, etc. Now here this is negative so what I did. Okay, here this will be negative or something, yeah. Yeah. Okay. There's some sign mistake here. It's U1, V2, da 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 da. This is U1, Vn, da da da. So this is U2, Vn, etc. etc. So what we did is we write Gram-Schmidt as matrix form. So it's V equal to U times upper triangular matrix. Okay. T is upper triangular. T is upper triangular. T is upper triangular. So you can write so given an invertible matrix, you can write it as a matrix times upper triangular matrix. Upper triangular matrix. Yeah. Okay. So there's some sign mistake here to be fixed. Be careful. Okay. So for instance, let's write V2. V2. Okay, use column picture. This will be U1 times V2 U1 plus U2 times V2 U2. Okay, etc. etc. Okay, etc. etc. Okay. Homework for this section. Homework for this section. The goal for this section is given a set of vectors, linear independent vectors, you should know how to use Gram-Schmidt to write the thing as also normal basis. So number 11, number 12, number 17, number 18, number 24. Okay. All right. Now we are done with chapter 4. Now we talk about chapter 5, determinant. Chapter 5 is actually important chapter. Okay. Now, given a matrix A, okay, so this chapter 5. Okay. So let's start with chapter 5. Determinant. Okay. Given a square matrix, okay, suppose we have a square matrix. A square matrix. Remember, a matrix gives us a rule that you plug in a vector, output a vector. So given a square matrix A, in column picture A1, AN. In column picture. Okay. Then we have the first column is the output. So if we plug in E1, which is a 1, 0, bounce of 0. Now if we plug in the thing to the machine A, the output is the first column. Okay, the image is the first column. Now E2 is the first is 0, the second component is 1, then a bounce of 0. Then you plug into A, so A multiply E2. Then what you get is the second column, etc. etc. Now this is En, 0 bounds of 1. This is A, and this is An. Okay. Okay, the left side, E1, E2, En, they are orthogonal. They are orthogonal. So if you believe that, you know, for dimension 2, area of a square is, you know, area of a square is 1 times 1, so we get 1. Okay. Now for dimension 3, if we have a box with length 1, so its volume will be 1 times 1 times 1, so we get 1. So we assume that, so the left side has area 1. So the left side, E1, E2, En correspond to a unit, okay, the unit n cube. So the matrix A maps the unit cube the unit n cube, n-dimensional cube. It should not, how do I see this? N-dimensional box, unit n-dimensional box, unit n-dimensional. Let's call it a box, dimensional box. Okay, n-dimensional box. Map this thing, the box, into n-dimensional n-dimensional object, n-dimensional. So if dimension 2, it is a parallelogram. Okay. Now in dimension 3, then we call it a parallelepiped. Now in higher dimension, then we call it this name, this word, parallelotope. 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 Okay, parallelotope. Now in dimension 2, we get a parallelogram. In dimension 3, we call it a parallelepiped. Okay. In dimension 3, the word is parallelepiped. In dimension 3. Okay, let me plot a picture maybe. Plot a picture. For instance, if we have this, this is the y, x, y. This is the y. Okay, for instance, let's just try the most easier case. For instance, A is, for instance, x, we map it to x. Y, we map it to x plus y. Y, so this is x. So we get this EY. I map it to I. J map it to I plus J. So this will be so this unit square map it to by the matrix A. By the matrix A, it maps to J will map to I plus J. So this will be I is I. Let's use the red to produce the image. Okay. Now J map to I plus J. I plus J. So this will be, so here this is red. Red maps to red. Okay. Now X direction, let's use another color. Let's see if we have green. So X direction, we have this green. I think X direction, it just fixed, so it's green. Now it's map it to this thing. Then it's complete a parallelogram. Let's use black. So the volume, so you see, we finally get this. So this is what we get. So the image of this square, we get a parallelogram. Okay. Now, if you have this first three-dimensional, maybe let's plot a picture for three-dimensional. So this is the y x. This is y. Here this is the y. So here this point is this is y1. This point should be 2y. Okay, now let's plot a box. So three-dimensional, let's plot. Now three-dimensional y. Okay. So three-dimensional, the box. Okay, so this is the box, three-dimensional box. Now, for instance, the A is, let's do it like this. X is just X. X is just X. So I will be I, J will be J. Z will be, K we map it to, for instance, G plus K. G plus K. Okay. So this will be, looks like this. So this matrix will be IJ, K is 1, 1. Okay. So this is matrix A. Now under this matrix A, under this matrix Z, then we don't have a perfect box. We have parallelogram, parallelepiped. So it will be looks like this. So XY is fixed, but Z is now changed. Okay, so XY is fixed here. Now Z is, we don't have here, Z will becomes, K will become G plus K. So it will be translated G. So it will be like this. But here it's this, looks like this. It's hard to plot. My plot is not good enough. Okay, you can imagine. Okay, so it will be a parallelepiped. So my translation is too much. So this will be look like this. Okay, I hope it somehow shows something. Okay, to have you let's maybe do it like this, maybe easier. Okay, so this direction is this. This direction is here. Somehow it's not very elegant. Okay. Okay, so this will be a parallelepiped. Okay, now we want to find the volume change of the volume. Now we the determinant we haven't defined. First of all, the determinant of this matrix is actually plus minus the volume, of this parallelepiped. Now the volume is a positive number. Why it's positive or negative? The negative, we get negative value if we flip direction. Okay, if we flip direction, then we get if we get a positive value, then we don't flip direction. Okay, flip direction. For instance, A is X is negative Y, Y is Y. So what we did for this A, what this matrix A does is I goes to negative I, okay, J goes to J. So if you have a square XY, X, now it'll flip. It'll flip the direction. Why? It'll flip the direction. Okay. Okay, now green part is fixed, but the red part is flipped. The red part is flipped. Okay, now you see, if you rotate it, use your hand, right hand rule, use the hand. use the finger go cross, rotate it from the red to green, okay? Then your thumb pointing outward for the first one, for the first square. Your thumb should pointing out of the screen, okay? So this direction. Now for the second, if you go across, use the finger to go through, go across red to green. Then your thumb pointing towards inside the screen. So the direction is actually flipped. So in this case, the volume does not change, the direction flipped. So you check the determinant of A is actually -1. So we haven't, although we don't determine, we give definition of determinant yet. Okay, so now we determine what the determinant should be defined, the explicit form, how determinant it should be defined. First of all, if determinant is 0, if the volume is 0, means they do not span the whole thing. So there should be some vectors that are linearly dependent. Okay, so if determinant of A is 0, okay, if determinant of A is 0, this means the column vectors does not span Rn. Then the column vectors does not span, column vector does not span Rn, which means the n column vectors should be linearly dependent. Column vectors are linearly dependent. Now, if they are linearly dependent, which tells us that A is not invertible. A is not invertible. Here we are talking about a square matrix. Invertible. Okay, now let's determine what the definition of a determinant should be. So we need to determine what is this explicit definition of a determinant. Now, of course, I can give you directly, but if I give you it just, from nowhere, you have no idea where this is coming from. So suppose we have this matrix A as this. Let's suppose A is this 2 by 2 matrix. A, B, C, D. Okay, this means we have 2 vectors, AC, and we have BD. Okay, AC, BD. So then we get, so suppose we get here A prime is AC. Here we have B prime, which is CD. Now the parallelogram. Now this is here, this is map of this thing. We have the thing. Unit square here, this is O, this is A, this is B. Okay, so it A map to A prime, B map to B prime under the map A. Now we need to determine, so this square, the square has area 1. Now we need to find the area of the parallelogram. Now area of parallelogram is area of the parallelogram. So let's see. O, the parallelogram. So parallelogram A, A is overused. So this OA prime times OB prime times the angle between them, okay, times sine theta. So suppose this area is S. Okay. Now we see S squared is OA prime squared OB prime squared times sine squared theta. Now sine squared we can write as 1 minus cosine squared. So this will be 1 minus cosine squared. Okay, so it's OA prime squared times OB prime squared times the thing. Now if you distribute, so you get OA prime squared times OB prime squared. Subtract, this will be OA dot product with OB squared, also value squared. Okay, use the definition of dot product. Okay, norm, product of norm times cosine theta gives us dot product, and then we find the dot product squared. So OA OB, so we have the coordinate. So OA will be OA squared will be A squared plus A is AC. Okay, A squared plus did I write it wrong? Okay, please right. A squared plus OA AC squared times OB is B squared plus D squared minus OA times OB dot product. You can write down dot product. Okay, dot product. So this will be A. This is the BD here. Okay, OA dot product with OB prime. So this will be AB plus CD squared. Okay, finally, if you work out the algebra, oh, sorry, there's no square here. Okay, this, if you work out by algebra, so this will be A squared distribute plus A squared D squared plus C squared B squared plus C squared D squared. Now, the second term, then what you get is minus A squared B squared minus 2ABCD minus C squared D squared. Okay, if you cancel terms, so you have A squared B squared, they cancel each other. Okay, now C squared D squared, they cancel each other. So what finally remains is this is A squared D squared plus C squared B squared minus 2ABCD. Okay, this is exactly AD minus BC squared. Okay, the area, if you take a square root, so the area will be AD minus BC, Okay. Now, so a possible definition for determinant, okay, the volume of the parallelogram. So we still needed some more work to show this determinant of AD, ABCD of this matrix should be, AD minus BC. So there are still a little more work to do. Okay. Another choice is negative of this value. Negative this value, then you will have problem because the identity matrix should be, we get the determinant of the identity matrix, it fix everything. So it should be get a 1. We should get 1. So you can check that case. So the negative value of this value is not a valid definition. So this is, a definition that we should use. So, okay, so this is actually, we define it to be the thing. And you see this definition is, is not artificial. It should be a natural choice to define. We don't have any better choice to define. So this is the choice that we should define. Okay. So 2 by 2 determinant. Okay. Now we talk about this example. So if A is rotation matrix, remember we defined the rotation. A is, we already defined the rotation. So this comes from the rotation matrix. Remember, rotation does not change the area. Okay, rotation does not change the relative direction. Relative direction. So you see determinant of A. Then what do you get? According to the rule, according to the definition, AD minus BC. So you get this is cosine times cosine AD. Okay, A times D minus BC. B is negative sine. C is sine theta. So you get a cosine squared plus sine squared, which is 1. Okay, this means geometrically this means rotation does not change the area. Okay, fixes the area of the unit square. And also, moreover, we do not flip the direction. Okay, we still get the same direction, relative direction. Okay. Okay. Now we know how to do dimension 2. Definition of 2 by 2 matrix. Now, what happens if we have dimension 3? What should we do if we have dimension 3? Okay, for dimension 3, what definitions that we should use to define determinant of a 3 by 3 matrix? Now, actually, we now try to find a definition that makes sense. Okay. Okay, now let's do the dimension 3 case. Let's now find a definition of determinant for dimension 3 case. Okay, now we start with this operation, cross product. Okay, the cross product, remember cross product is only defined in dimension 2 and 3, dimension 3 in R3. Okay, now we define the cross product for A, B in R3. We take two vectors in R3, we define the cross product. The cross product. Now for inner product, we define inner product, okay, or dot product. Now here we define another operation, cross product. So the output is a vector in R3. So it's a vector in R3. So this cross product is a vector, as the vector. Now to determine a vector, we need to define its direction and its magnitude as this vector, as a vector perpendicular to both, perpendicular to A and B. Okay, of magnitude A norm, B norm, sine theta. Theta is the angle between the two vectors. Where is, now we determine the direction in a moment, where theta is the angle between A and B. Between A and B. Okay. Now the direction. Now we determine the direction. The direction is determined by the right-hand rule. Okay. Its direction. So its direction is determined by the right-hand rule. Right-hand rule. I.e., if your fingers, okay, if fingers of your right hand curve in the direction of rotation from A to B, now your thumb points to the direction of A cross B. I.e., if fingers of your right hand curve in the direction of a rotation from A to B. Then now angle should less than 180. Then your thumb will point towards the direction of A plus B. The direction A cross B. Now we determined the direction A cross B, okay, by the right-hand rule. Okay, you can easily check some property of the cross product. Properties of cross product. Okay, first of all, A cross B equal to negative B cross A. So the vector flip the direction if A cross B, if you flip the thing. So its cross product is not commutative. Be careful. So if you take B equal to A, you see A cross A equals negative A cross A. A vector equals negative of this vector. This means this should be 0. Okay. And then you use I cross J, you get a K. Okay. Okay, this is why when we plot coordinate in XYZ R3, we always plot the right hand coordinate. Okay, so this is a right hand. Okay, I, J, so XYZ, I, J, K. Okay, so this is XYZ. Now, you see the direction X, let me let X be red, and Y be green. So if you rotate the rotation from red to green, so if you curve your finger of your right hand from the red to green, okay, now your thumb will pointing towards to the direction of Z, okay, so this is right hand right hand coordinate. So this we get a right hand coordinate, right hand frame. Okay, right hand coordinate or right hand frame. Now, if you do it like this, this is x, this is the this is y, this is z. So this will be a left hand. If you switch x with z, switch x with y, then actually you get a left hand coordinate. It's not wrong. It's not wrong. Left hand coordinate, but it's unconventional because the right hand coordinate is all conventional. Okay. 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 So another property. Continue. G cross K, we get I. K dot with I, we get a J. Okay. To remember this, that's easy. If you write IJK, if you rotate this, okay, then you rotate it, then you circle this around. IJ, you get a K, JK, you get an I, KI, you get a J. Okay, so you get a cycle. Okay, another property. Okay, now if you have A, first of all, A cross B will be the area of the parallelogram. Okay, you can check with the definition of the parallelogram. Area formula of a parallelogram. Okay, side product of the two sides and times the sine theta between them. So this actually norm of this cross product gives the area of the parallelogram determined by the two sides, with two sides determined by A and B. Area of the parallelogram. With two sides determined by A and B. Determined by A and B. By A and B. Okay. Okay, now, for example, if A is, let's see, x1, y1, B is x2, y2. Okay, so this will be xi, x1i plus y1j. And this will be x2i plus y2j. Now, if you do cross product, A cross B, of course, we also have the distributive law, which is this I forgot to write. A cross B times B, A cross B plus C is A cross B plus A cross C. Now, another factor, you can also distribute, we also have a distributive law for the other factor. Is a switch them by multiply by -1. You get the other distributive law for that another factor. Okay, so now we use distributive law. So we get this is a x1i plus y1j cross x2i plus y2j. Now, if you distribute this, what do you finally get? Okay, I cross I is 0. Okay, I cross I is 0. So there's no I cross I. So and then I cross j. So we have x1, y2, I cross j. Then we get a key. Now y1g times x2i, so g cross I. Remember, g cross g, we get a 0, so that's gone. Okay, so I cross g, we get a k. So it's x1, y2, k, plus, no, g plus g cross I is negative I cross g. So this is the minus y1, x2, k. Okay, so this will be x1, y2 minus y1, x2, k. Okay, now it's norm. It's norm. A cross B norm will be exactly this value. K has norm 1. This x1, y2 minus y1, x2. Okay, so this is, if you remember, if you what we just did is we already did this. If this is a vector A, this vector B, then it determines a parallelogram. So suppose this is the x1, y1. This is x2, y2. Then the area of the parallelogram is you know, x1, y2 minus y2, y1, x2. Okay. Okay. Now, if you have, so this is in the plane, in the xy plane, okay, in the xy plane. Now we did this, use cross product. You see, we also use the inner product. Last time we actually used inner product to find this, okay. This is how we derive the area, use inner product. This is how we define as cross product. You see, they will look like exactly the same form if you switch the variable. Okay. Now we can actually extend this to 3-dimensional vectors. Now we determine the case, we have 2 variables. Now if we have 3 variables, A is, let's see, this is more complicated now, x1, y1, z1. AB is x2, y2, z2. So if you write coordinate form, so this x1i plus y1g plus z1k. Okay, now this will be x2i plus y2g plus z2k. Okay, now if you work out by algebra, A cross B by algebra, what you finally get is, remember, I cross I is 0. So you can only I cross G, I cross K. So let's look at I cross G. I cross G, so we get a K, okay? So let's find the vector that we produce K. IG, we produce K. So then you need a, let me just multiply them together. So this will be x1i plus y1g plus z1k cross product with x2i plus y2g plus z2k. Now, if you distribute this cross product, now the first term xyi, you cross I, you get nothing. So you cross G, you get K. So you get the coefficient of K comes from the contribution x1 term times y2 term. Ig, you get a K. Now you have another case, i.e. y1g, G with I. Okay, this also produce K. Okay, but it's G and I. Gi, you switch Ig, you get so G cross I, you get a negative K. So you get actually that term, so you get a negative contribution. Okay, similarly, you work out work out the term that for G, okay? So you get Z1, you can just work out similarly. X1, Z2, plus the term that with I. So it's a Y1, Z2 minus Y2, Z1, I. Okay. So so this you can write as I times Y1, Z2, Z1, Y2. So remember, this is the two-dimensional determinant. Okay, we defined the two-dimensional determinant already. Okay, so this will be minus G here. The second term will be X1, Z1, X2, Z2. Now this will be K X1, Y1, X2, Z2. Okay, so we define as this. We define it to be the 3 by 3 determinant, IJK. So we define this thing to be equivalent. X1, Y1, Z1. X2, Y2, Z2. Okay. So the right, we define it to be the thing. Define it to be the sum of the three terms. Define it to be that thing. Okay, so this is the cross product of two vectors A and B. So for example, let's do an example. So A to be this, A to be this. 1, 3, 4. B to be 2, 7, 5. Okay, if you do cross product, A cross B, so you put IJK. So because the form is, you know, there are too many variables, it's easy to get confused. Okay, we human beings is not good at deal with tedious, you know, tedious thing. It's better to use computer. Now we, you know, to have a better, you know, memory, to better memorize the thing, we use more symmetric thing. Okay, IJK, so A is 1, 3, 4. Remember a rule is easier than remember the result. Okay, you can just remember the rule, and once you want to compute the result. So the coefficient of I is I. Once you get I, you cross out the rule and the column that contains I. Okay, then you get the remaining is 2 by 2, 3, 5, 4, 7. Okay, so what do you get here? You cross out the line with I and with the columns that are with I. So what remaining is the red. Okay, if you cross out, so what is remaining is the remaining is this. So you get the red. So you get the red. Okay, determinant of the red. Okay. Now for minus, once you get G, let's use green. Minus G. G is you cross out the rule and the column. Rule and the column of G. So what you get is this and this. Okay. So you get 1, 2, 4, -5. And once you have key, you cross out the key, cross out the rule and the column that has key. Then what the remaining is, let's use another color. Let's use blue. So if you cross out the key, what remaining is the blue part. Okay, cross out the rule that has key and the column that has key. So this is what you cross out. So the remaining is the circle, the blue circle. So it's a plus key, 1, 2, 3, 7. And this is easier to remember. This is easier to remember, okay? Once you get that, then you compute that, use 2 by 2 determinant. Use 2 by 2 determinant. Then this you get finally, 2 by 2 determinant we already defined. So finally you get negative 33i plus 13g plus k, okay? So the area of the parallelogram determined by A and B is the area. Find the norm. So this will be square roots, negative 43 squared plus 13 squared plus 1 squared. Then you compute this thing. Finally, you get a 2019 square root. Okay, so this gives us the area of this parallelogram. Okay, this can be generalized to, higher dimension n. Okay, now we don't have time to talk about the n-dimensional volume. Next time we will talk about how we generalize to n-dimensional thing and give a definition of a determinant for n by n matrix.